Bugünkü bölümde akışı şu şekilde planladık. Öncelikle Profesör Englekirk ve Profesör Barbosa yöntemleriyle ilgili hatırlatma ve belki bir miktar daha derinleştirme anlamında birer sunum yapacaklar ve bu sunumlar sırasında ilk gün için size göndermiş olduğumuz ders notu 1 ve 2 içeriği, bir miktar raporla ilgili bilgiler ve bunun ötesinde de örnek yapı 1 ve örnek yapı 3 ile ilgili ilave bilgi aktarımı yapılacak. Anlatımlar bittikten sonra sizlere göndermiş olduğumuz işte sunum dosyaları üzerinden eğer sormak istedikleriniz varsa yaklaşık olarak hani 1,5 saat civarındaki bir zaman diliminde hani 12.30'da tamamlamayı planlıyoruz. O sürece kadar karşılıklı tartışma şeklinde ilerleyecek. Bu tartışmaları yönetmek üzere Sayın Profesör Doktor Faruk Karadoğan hocamızı ben kürsüye davet ediyorum. Çalışma boyunca toplantının moderasyonunu kendisi yapacak. Öncelikli olarak yöntemle ilgili bilgi vermek üzere hangi hocamız konuşma yapmak istiyordu? Evet, Profesör Englekirk'ten rica edelim.
Can I say a couple of things before you start?
Oh, please.
Thank you. Ladies and gentlemen, it is very nice to be with you. It's my honor to be with you, actually. And I would like to taking this opportunity to the professors who are going to summarize right now the technique they are proposing, actually. And I will be pleased again because I didn't have a chance to be here in the first 2 days of the seminar. Maybe there are some other newcomers here, so this will be good for them as well. So it is very nice to hear that directly from Professor Kierkegaard. Okay. Floor is yours. Go ahead, please.
Thank you very much. It's good to see you back again. My first task is to tell you in 5 minutes what took an hour and a half yesterday and the day before. But I think I can do that very quickly. There's a misconception in the world, I think, that in the United States we use the Uniform Building Code and our codes to design buildings. Not the case. We have not used the code to design high-rise buildings for 40 years. How that happened was pretty simple. I introduced the concept of using what is now objective-based design, and the building department approved the process. Why? Because the head of the building department was a student of mine. So once that came in, everything shifted. So the concept that we use the Uniform Building Code to design buildings that are over 150 feet is totally wrong. It does not work. What we go to is what I call a scientific procedure. Right now, you see the acceleration response spectra, and the thing that you see most notably about that is the fact that it is a sloping line. So okay. It's a sloping line. So the designer has to figure out exactly what the period is before he can design the building to an acceleration level. The other thing that you see in the response spectra is it starts up here with 2G and runs all the way down to a lower value of 0.4. So the codes try to manufacture factors that account for ductility, damping, blah, blah, blah, blah, blah, have no basis in science, and follow this sloping line. Has no scientific basis, no rational basis, and it can't produce a building because the force demand is so great. So what change did I propose? I proposed going to a velocity spectrum. Here you see the spectral velocity. And regardless of the level of the earthquake, there is a consistency across here. Not in this. I can't work even a telephone. So, oh, there we go. You see how it's constant. You can draw a constant line through each one of these. Yes, it varies a little bit, but not very much. Even with a very large earthquake, there's still a consistency in the spectral velocity. So that's the whole key to objective-based design, is you have a constant forcing function. You don't have one that you try to manufacture a design basis from. Okay? Where are we going now? And the same thing is true if you use a displacement base. Here's a response spectrum for the earthquake based on the displacement. If you project the displacement used on this, you have to figure out where you are, because you're somewhere between 0.4 meters and 0.8 meters. So you have to anticipate where the building period is if you're going to even design to a displacement base. So the answer that I proposed was that you use the constant velocity. Now you pick a constant velocity and design based on that. And you say, how can you design to a velocity? Well, it's really quite easy, and there are just 3 simple equations in the step. You don't have to predict the ductility of the system. You don't have to predict the damping in the system. Nothing. You just follow that forcing line and use 3 equations. These are the simple representations of the equation. The first step is to identify an objective period. So what your design is based on is looking for the system that has the characteristic period that optimizes your design. So you're looking for a period or the dynamic signature of a building that gives you the best possible performance. The equation is simple. The one variable here is you ask yourself, how much would I like the building to displace during an earthquake? So you make up your mind. Some people say 1%, 2%, 3%, 4%, 5%. So you pick that level. You say, I don't think it's a good idea for the building to displace more than 2%. Bang, one number. This is a factor that converts the displacement target from a multi-degree of freedom system like a building to a single degree of freedom system. So you take it from a multi-degree, immediately reduce it to a single degree of freedom system, divided by your forcing function, the spectrum velocity. And what do you get? You get a trial period. So now the design process is for you to measure your building's period until it comes close to what your target is. Now, what could be simpler than that? If you design a building, how much would you like it to displace? How much would you like it to drift? 6%? Well, that's a little much, but because what does that mean? In a 100-story building, it's going to move over 6 feet. Oh, you probably don't want that. But the target drift that we've become to accept is 2.5%. The codes now are requiring a design period must be less than 0.8 of a, now what is it now, 1.6%, 1.8%? I can't keep up with the code, so what is it, Andre? 1.6, 1.8, target drift?
Target drift, it depends on the building height. So
okay, a function of the building height, so now, but it...
Up to 4 stories is 2.5. 5 stories is 2.
5 stories is 2, 6 stories is 1.9, blah, blah, blah. So, but rationally, 2.5% is what we use. So this is the procedure we've used in Los Angeles for 40 years. Why? Because the building department official was a student of mine. This is the usual thing that you're shown in dynamics classes, I believe, and it actually appears in a book that I wrote in 1994. It's called a response spectra that tells you, identifies the lines that we talked about. And the line that I showed you was the spectrum velocity. And it refers to a small constant region here. It's very misleading. Why is it misleading? This is a log scale, so they can get it on one chart. Has nothing to do with anything but a conversion to graphics. But it gives you the wrong impression. Can we just go back one more? It indicates, look, this looks so much more than that. But that's misleading only because they chose to use the logarithmic scale. In reality, here is the acceleration constant region, somewhere around 0.5 seconds. The displacement constant region stretches from 0.5 seconds out to a period of about 4 seconds. So it dominates the building response. What happens in the objective-based design is geared to reach what your objective was. Do you want your building to be so rigid that it accelerates? In other words, if I pick this period here, as I move this way, the acceleration increases. Until I get here, it is acceleration dominated. And as I think I mentioned, a lot of the buildings that we do design, nobody designs them. They design the building and then it performs. But the acceleration in the roof is 2.5 times the force of gravity. 2.5 times the force of gravity. Do you want to sell somebody an apartment on the 15th floor that has 2.5 G acceleration? Only if you want to go to the moon. Otherwise, you don't want it. So the objective is to get as close to your target as possible. So the science is simple, but it is science. It's based entirely on dynamics. You see nothing in here about damping, displacement, ductility, anything. That is not a variable. Now, this is not a new concept. I'm not taking advantage of that. All I did was listen to people who were much more knowledgeable than I that said, Strength has nothing to do with response. Well, the rest goes through the simplicity of the process. That magical gamma factor is nothing more than a mathematical representation that describes the difference between a response of a single degree of freedom and a multi-degree of freedom. So there's no magic to it. Nobody has to guess. It's all there. The book that you have available, shall I stop?
No, please go.
The SSRP, it was a test of a 5-story building, 60 feet tall, 20 meters tall, that we tested on the shake table at UCSD. And what we did is confirm every bit of the analysis in the response. In other words, we used exactly the same ground motion into the table that generated all of the factors, and we were within 1 or 2% of predicting what the response was. So, and there was no mystery to it, no speculation, no code votes, no, nothing. Pure science. I think that's about all I said. Is that right?
Yep.
Good. You have any questions?
I would like to ask to the audience, do you have any questions regarding these explanations? Actually, don't hesitate to ask any question because this is a kind of workshop. So we are going to discuss, and it will be much more valuable if you have more questions asked. Okay, go ahead, please.
You see, I've converted them all. Right? Oh, one.
Türkçe soracağım, Atabey çevirebilir misin? Bu dün Precast bir yapı üzerinde de çalışma yapmıştık. Orada da sizin işte zaman tanım aralığında yaptığınız bir çalışma da var tekrar onun üstüne. Bu gamma faktörünün kullanımında işte bizim yaptığımız tek katlı sanayi yapılarının yüksekliği normal konutlu yapıların yüksekliğinden farklı. Hani dünkü yapımız 8 metreydi. O serbestlik derece, yani çok serbestlik dereceli bir yapının tek serbestlik dereceli bir yapıya çevrilmesiyle ilgili formüldeki gamma yükseklikten bağımsız mı? Hani tek katlı yüksek bir yapıda daha farklı olması gerekiyor mu? Ya da bu formülde bir değişiklik gerekiyor mu?
Professor Englekirk,
Evet.
the question is about the model participation factor gamma. This coefficient. This is a simplification of the gamma factor. So the question is about, does it depend on the height of the building?
If you have a 100-story building, what is that number?
100 katlı bir binanız olsaydı bu gamma da nasıl bir değer elde ederdiniz diye soruyor.
1.5. Evet.
What?
1.5.
For a 100-story building? 3n times 2n plus 1?
Tamam,
I'm
bu
sorry.
zaten çok katlı binalar için geliştirildiğini biliyoruz.
1.5.
Ama entegrasyon için, hani biz kendi yapılarımızda kullanım için yükseklik bazlı bir şey önemli mi? Yani
He asks if it depends on the height of the building.
No, it's okay.
Professor, the question actually is in precast buildings, the story heights are like 8 to 10 meters.
Okay.
This formulation is typical, I guess, for a residential building, which the floor heights are 3 to 4 meters. So in a 100 floor building, you have 100 divided by 50, which gives you 1.5. But in a precast building, which is 10 meters high, but it's still one floor. So the question is the floor height dependent on this formulation?
No.
Or does it have an effect?
No. The assumption in developing this factor is a concentration of mass at a node.
Okay. So it's a lumped mass on the column. It doesn't matter the height of the column. It's just a single cantilever. Okay. That's the question, actually. Yeah. Thank you very much.
Yeah, so the way, I would just add, the way this was derived, right, you go back, to the 450 set, it's constant height and lumped masses across the height of the building. So that's the basis. So you could develop, if there are particular buildings that have, for example, much higher story heights and then shorter story heights, you could develop approximate equations, but it's all analytical, the way these are derived. So you could develop specific ones for the types of buildings that are most useful in a particular system. But this is constant height and lumped mass.
Otherwise, it's not always the height of the floors are not always the same. So it's another question what to do in that
right,
case.
but you can
make a correction or just keep on using the approximation. This is an approximate method in the end.
You should use a better approximation, right? And the better approximation is either, again, ask one of the professors here to develop that factor for you, or ask us to develop that factor for what would be typical cases that you're most interested in. And once you have that analytical equation, you can do that.
But
yeah.
Yeah, but I think the important thing is that it's a small range. It can't get higher than 1.5, and it's typically for a single story. It was developed by Chopra over 70, 80 years ago. I didn't make the derivation.
Yes, go ahead.
Professor Englekirk, I understand that you basically say that let the buildings sway until 2% drift, right? In order to prevent the excavations, basically.
I'm afraid
you didn't
my
get it?
old ears won't pick that up.
All right. I understand that you basically say that let the buildings sway, move during earthquakes, right?
Yeah.
So until 1% of drift. That's okay, but how about the reusability of the buildings after an earthquake? Is there any concern that you had experienced in terms of the reuse of earthquake in your time? Because you said that you've been designing buildings for over 40 years, and probably your buildings experienced lots of earthquakes in California.
Our codes in Southern California require that the content, like the cladding or anything that has to do with sensitivity to drift, be able to withstand a 2.5% drift.
Yeah.
So if you clad your building in glass, that glass must be able to move 2.5%. And during the Northridge earthquake, I walked by one of my buildings and you couldn't even see that there was any damage.
With that.
The only thing that you have that is an impossibility is an elevator. Because if you displace 2.5%, the elevator doesn't understand that motion.
So you say that there is no significant residual drifts after the earthquake?
Oh yeah, I think so.
You think so? Okay, thank you.
We had problems with steel frame buildings that were poorly, the product was poor. It couldn't take the displacement. We knew that, but we couldn't convince the steel industry of the problem. I think with precast concrete and cast in place concrete, 2.5% is not a problem.
Can I add something? So are you setting a performance limit for that level of drift? Is it a life safety or controlled damage or what?
Well, if the systems in the building are designed to take 2.5% without damage, then it's a performance-based. If the systems cannot take 0.5% and you force it to 2.5, you're going to have to fix them.
So you can totally define.
Mr. Barbosa, just a second. Is the question clear, or would it be possible to be translated into Turkish? Is it clear?
Yes.
Okay, fine. Go ahead, please.
Thank you. I was just going to add, it's exactly what you're pointing to. You can pick the performance that you want based on the systems. And if you have a hospital, for example, you may want to have different targets for that design level. But I think what's being suggested is that you can pick the number depending on what type of structure or what system, what performance you want to get. But it's also very clear that you have to think about your non-structural elements as well as part of the performance of the building system.
Usually, the acceleration generated in the building is more a problem than the displacement. I don't know. Go back to that. Yeah, no, whoop, one more. If you notice, if you make the building stiffer, the acceleration goes up. This is a tripartite plot with displacement on this angle and acceleration on this. So the reason for optimizing based on the period is to find the proper balance between induced acceleration and induced displacement. So objectively, it's better if you can control the behavior of your components to take a 2.5% drift. Then you reduce the acceleration. Ideally, if I could design a building to 5% here, the acceleration would be basically nothing. So that's why you pick the objective, and all you're asked to pick is the objective. Imagine a 100-story building. Would you design that to 2%? No. And why? Because it experiences no acceleration at all. It's a base isolated, right? So that's why the key to it is setting a period, developing a building with a period that optimizes performance. You want the proper balance between acceleration and displacement, or story drift, if you prefer. But like I said, our criteria and our suppliers understand they have to go to 2.5% story drift, and they have done that.
Are there some other questions? Okay. If there is any other question, I would like to forward a simple question to Professor Englekirk. He's a very experienced structural engineer. He designed very important buildings in the United States. When he is trying to put the period to the target, it means that he's going to play on the rigidities of the elements. If he wants to catch up the period he proposed or he is supposed to have it, he can use simple columns or shear walls. If he chooses columns, or a lot of columns, of course, the tendency of the structural behavior goes to a shear deformation. But as soon as he combines this one with a shear wall to obtain the target period, and if he chooses some shear walls, then the tendency of the structural behavior goes to bending. So, in the first solution, the relative displacements will be bigger in the lower stories. In the second solution, the relative displacement will be bigger in the upper stories, as it is known. So, could you tell us something about what is your preference? How you are going to provide the period through the stiffnesses of the elements? Are you going to choose columns more or shear walls, or what do you think about that?
Well, that's a designer's problem, and it has to blend with the function of the building. If shear walls are a functional mandate, then you have to look a little deeper, but the same principles apply. In other words, if I have a shear wall building and it has a period that's 1 second, and I cannot get it above that, then I have to make sure that I design the base to be able to deform that amount. In other words, instead of, well, let's see, where's that?
Which one?
The one that shows the deformation of the plastic hinge formation
in the tests?
Yeah. Keep going.
It's in the other presentation, maybe.
Maybe it's in the afternoon presentation. But the designer can manage this situation. For example, one of the things that you do is you can move the reinforcing to the middle of the shear wall. You can play with the shear wall, and this is what you control. In a frame building, you have large rotation here, which you cannot get away from. The same thing is true with a shear wall. How do you manage a shear wall when you have a large deformation there? In the frame building that we constructed and tested, we got all the way to 6% rotation, 0.06 radian, and in the base of the column. There's no way to get around that. So you have to make sure that this connection can take that. And that was the only place that we had any damage. And the reason we had damage there was because somebody left out one of the confining ties. So the designer in a shear wall building has to be concerned with the impact the displacement has on the structure. And in the many, many pages, the 1,000 pages that I've written, I've shown the difference, for example, on a shear wall. Instead of putting the reinforcing out here for the tension, I take this reinforcing, that reinforcing, put it in the middle where it's less vulnerable. Or I use post-tensioning and look at the behavior, but still you know what the deformation is, so you design to that. I don't know if that addresses your... Once you know what it's going to be, then it's up to you to provide it. And if you can't, then you change the program.
Okay, thank you. Yes, go ahead, please.
Ben pedagojik olarak, çünkü hoca olarak da yıllarca şey yapayım, tamam. Hocanın ne? Yok abi. Neyse. Bu OPD konusunu mesela hocalar lisans seviyesinde aktarabilecek bir nosyon olarak görürler mi? Yani imkanları olsa bir fakülte dese ki biz inşaat mühendisliği bölümüne lisansta böyle bir şey katmak istiyoruz ama yani hep şey konuşuyoruz ya, ivme spektrumu, R katsayıları, şunlar bunlar, bunların hepsi fazlalık. Sadeleşmeye hani çalışıyoruz bu 2-3 günde. Pedagojik olarak sizce inşaat mühendisliği öğrencilerine böyle bir şey lisansta verilse böyle bir şey düşünür müydü? Yoksa bu konu önce bütün yanlışları bir öğrenelim, tırnak içinde tabii söylüyorum bunu. Sonra yüksek lisans seviyesinde belki bunları hazmetmek daha doğru olur muydu gibi bir eğitimcinin gözünden sadece merak ettim. Sağ olun, sizi yordum, kusura bakmayın.
Faruk hocam müsaadenizle. The question is about how this methodology can be taught in universities. Do you think in undergrad education OBD could be taught, or maybe it is a little bit too advanced, so it should be taught in grad level? What do you think? What is your projection in terms of point of education in civil and structural engineering?
Don't smile. My answer is to make sure that you advance the students that can understand it and make sure they do. What we do now is we try and teach everybody, but it's like me. I can't operate a telephone. So you have to teach a certain number of people to do that. The thing is that it's much simpler to teach this than it is to say, well, you need a ductility factor of this, you need that, you need, this is the maximum period you can use, a whole bunch of arbitrary things. When I entered engineering, a long, long time ago, the El Centro earthquake was our model. And the first analysis that I did by computer and time history said the El Centro earthquake didn't even cause the structure to go into the inelastic range. I've seen our codes go to 100%. Can you imagine designing a building to 100% G? No. I think this is much easier than teaching somebody a table of factors. How many factors do we have now? I've stopped reading the codes 50 years ago. I don't know that that explains your system, or your problem, but it really comes from looking hard at our teaching program. When I did my undergraduate work, 1 out of 10 students in engineering graduated. 1 out of 10. Today, 100% graduate. Is that right? So it falls on the education department to make sure that people find where they should be. And it was the same thing in graduate school. Professors would quit if they had more than 6 or 8 students in a class.
Benim fikrime göre bu metodolojiyi öğretmek, yani mühendislik ön sezisinin daha ön planda olduğu bu metodolojiyi öğretmek, insanlara işte R katsayıları, süreklilik katsayıları, bazı tablolar vermekten daha kolay. Olabildiğince fazla kişiye öğretmemiz lazım. Bir de eğitimi biraz daha rafine hale getir. Bizim Amerika'da da böyle bir problemimiz var. Ben ilk öğretim görevliliğine başladığım zaman lisansüstü derecelerde 10 kişi oluyordu ve sadece bir kişi mezun olabiliyordu. Şimdi çok daha fazla kişi var ve hepsi mezun olup çıkıyorlar. Ben bunu bir problem olarak görüyorum diye.
That becomes a philosophical question. You can't teach me to operate a phone. Same thing would apply. I can't teach you to do dynamics without a little bit of understanding and making sure that you understand the basics.
Bu biraz da felsefi bir soru. Ben örneğin şu hala telefon bile kullanamıyorum diyor. Biraz da felsefi bir belki de bir generational bir sorun diyor.
Arkadaşımızın sorduğu soruya cevap verecek dinleyicimiz var mı acaba? Is there any audience in the room right now who can answer the question asked by this gentleman? If there is no, I would like to say a couple of things about that. Oh, go ahead please.
Şöyle, bence önemli bir soru bu. Ama şahsi görüşüm şu yönde. Her basitleştirmenin arkasında aslında çok ciddi bir tecrübenin olduğunu düşünüyorum. Dolayısıyla evet, hani bu basitleştirilmiş yöntemi lisans seviyesinde bir öğrenciye anlatmak belki kolay olabilir ama şöyle bir problem oluşabilir burada. Sezisel olarak hangi boyutta olmalıyım, ne yapmalıyım? Çünkü mesela bunun içinde de var aslında bir R faktörü. Dolayısıyla lisans seviyesinde bir öğrenci yani yapı nasıl davranacak? Bunu öngörmesi biraz zor olabilir. Yani biz aslında şu an bile bu R neden 8, bu R neden 7 gibi bir problem yaşıyorken böyle bir sistemde de aynı problemin olacağını düşünüyorum. Yani esas problem bence kavramsal olarak davranış esaslı tasarımı hissedebilmesi mühendisin. Ve bence Mr. Englekirk'ün söylediği çok önemli. Çok fazla sayıda öğrencinin mezun olması eğitim kalitesinin de aslında tüm dünya genelinde belki de biraz aşağı doğru gittiğini gösteriyor. Ve bu da mühendisliğin özünün bence sezisel olmaktan uzaklaştığını gösteriyor gibi bir sonuca varabilir diye düşünüyorum.
Putları yıkmak için önce onlara inanman lazım.
Evet, evet doğru.
Önce bir
Karşılıklı konuşmayalım isterseniz. Olur mu? Onu sonra kahve içerken yaparsınız. Bunu tercüme eder misiniz hocaya?
Tabii. Also, Mr. Furkan also agreed with your assessment of the educational quality, and it should be harder to graduate from grad and undergrad courses, degrees, and also an engineering intuition should be possessed by the engineer to implement this OBD behavior.
Okay. Ercan Hocam, bir ara vermeyi düşünüyor musunuz yoksa 12.30'a kadar devam ediyoruz? Evet, tamam. Now, there are two important structural designers in this room coming from far away. So, I would like to free you to ask any question you have, not only related with the topic we discussed right now, but you can forward some additional questions which are your problem. For instance, most of you are not only trying to design new buildings, but you are working on retrofitting of the structures. So, do you have any question related to the retrofitting problems based on our existing code? Do you have any question regarding that topic? If you don't mind, I would like to ask you a question about retrofitting, even if it is a little bit far away from the topic we were discussing. The existing structures, let's say 50 years, 60 years ago constructed on the Bosphorus, and they have very good sea view, etc. They have to repair right now. Are we going to take into consideration the earthquake forces equal to the new buildings to assess that existing buildings? Or are we able to reduce the forces we are going to take into consideration for that purpose? I know that you are not suggesting more stronger buildings, but some other things. But this is the case now in Turkey, in Istanbul especially. There are a lot of weakly designed old buildings, and the code we have says that they have to satisfy the conditions which are applicable to the new buildings. Is that correct or not?
When you deal with an existing building, it's important that you consider the real capacity of the building, what the members can sustain in terms of drift, whether there is a realistic load path. By that I mean, if you look at a building and you consider its condition and try to approximate what the ductility will do to the displacement. In other words, will it displace according to the way we're talking about here, and whether the components can withstand it. The problem that we get into in retrofit work and applying the code is the code will tell you how strong this connection has to be. And the real question is, how deformable is that connection? It has nothing to do with code and a strength-based procedure. The question is, do you think this connection is going to be subjected to 2% story drift? And whether that's rational or not, and whether it can sustain that 2%. If it's very brittle and it can't sustain 1%, then you have to do something to bring up that level of displacement, but not to an arbitrary length, strength. Does that answer your question? No?
There are some proposals done by San Francisco people. They say that roughly you can get 75% of the forces you use for new building to assess the existing building. Of course, the rotational capacities of each section, either from the beam or from the column, shouldn't be exceeded during that one. Or the relative displacement of the drifts shouldn't be exceeded than the proposed one. But what should be the forces we should take into consideration during the assessment stage? This is my question. Are we able to reduce it a little bit or not?
I would say you don't consider the forces at all. You consider the deformability of the connection. So a lot of the things that we do in Southern California, correct me if I'm wrong, is we try to improve the ductility of the member. So we try to develop a deformation that we can sustain. If we suspect, based on an analysis and the level of earthquake that we use for, that we need 1.5% rotation there, what the standard procedure is to try and get that level of deformability. Sometimes it's wrapped in a stressed casket or a case. What are the... Yeah, some kind of a jacket. Or you can put a jacket and pump grout into it to make the connector more deformable. Strength has little to do with it unless you have none at all.
I know that the method you are proposing based on velocity spectrum at the end provides less reinforcement we need. Is that right?
Exactly.
So now let us have a look at the problem from opposite direction. If your technique gives us lower reinforcements, does it mean that we can take into consideration lower forces to assess the building?
I guess my answer would be we don't consider the strength level at all. Can you show some of the cross sections maybe in the lecture 2?
These ones?
Yeah, anyone. These connections we tried. We put in maybe 10 different types of connectors to see what would happen. They were all designed to an effective strength of one reinforcement ratio of 1%, much lower than most. They all performed quite well. What we did take care of, as you can see here, we knew a plastic hinge was going to form there. So in a retrofit program, you don't look at the strength so much as you look at, you know where the deformation is going to be required, and you improve that. So for example, if I found this building in a retrofit program that had a tie here and a tie here and a tie there, I might say, okay, take the concrete out, put a tie in there. The alternative is, if it was reasonable, some people wrap it with a fiber. I guess
Yeah.
they stress it, don't they? I don't know how they do it. But in other words, you don't worry about the strength. If this is 1%, which is about what we shoot for in our design, the 1% reinforcement ratio, and we find that in an existing building, we just make sure that you can develop that 1% into the necessary deformation.
Is this example coming from a precast building or any kind of cast-in-place reinforced concrete building?
We use this connector in precast buildings.
Precast.
I just tested it here because we weren't precasting, but it's the same idea. You take all of the strain and put it here as opposed to there. So.
Okay.
Why do we put it there? Because I know I can protect its deformation.
Hocam programa göre bina 1 ve bina 3 üzerinden hızlıca geçmemiz gerekiyor. İsterseniz o yönde misafirlerimizi davet edelim. Could you make some brief summary about building 1 and building 3 with the help of Ata to evaluate the outcomes of the examples for the audience, okay?
You want me to leave? No? Oh.
So again, thank you everybody for having us, and it's been a fantastic 2 days, not 3 days of discussion. I really appreciate all the discussion and all the knowledge that you also have and the real problems that you're facing. Design example 1, this was a pretty regular building that we worked on, and about 4 meters, 5 stories high, 4 meters per story height. And then you can see the plan view over here. When we designed it, there were actually 3 designs that we worked on. There was the Turkish design, and thank you for that great presentation. Then we had the US co-design, and then we had the OBD design that we shared as well. I'm just jumping straight. We had a very good presentation on the Turkish design, jumping straight here to what I presented, which was on the US-based design and then the comparison at the end. So this followed ASC 716, ACI 318 as well. We had the same parameters that we actually analyzed all the 4 buildings in these 2 days of workshop. These were the acceleration and velocity, corresponding velocity spectra that were used. And this is for a site in Southern California. That was the basis of what was analyzed here. And in terms of the solutions here, we explained how in the US, we have the lateral force resisting systems and the gravity systems. And so we just compared what would be the need if it was a code-based design versus an OBD-based design. And essentially here you can see that for the code-based design, we ended up with a 3-bay, 5-story, 2 frames in each direction, so a total of 6 bays that we would need in each direction. When you go to OBD, because you set the target displacement, and the summary was that per code, we did have to use a 2% maximum interstory drift limit. And you can see there at the end that the corresponding base shear would be 0.15 times the weight, seismic weight of the building. And then the detailing was approximately around 1.2% there, and just taking care, making sure they have enough room to actually pour in concrete. I mentioned in the US that we've moved, especially for columns, and also beams, but especially for columns, at least we've moved to grade 80. So grade would be 550 megapascal to improve the congestion and therefore also improve the behavior of the building. In terms of the main steps in terms of coming up with a base shear, I really think, and even what Ata is going to show us again, he's got 6 lines or 7 lines. So the basic, the fundamentals are pretty simple to come up with the equations. There is at the end a factor when you want to bring in forces, right? So you start, set the displacement levels, you have the velocity, the target velocities, you have the displacements, you set the period, and then at the end, you have to define how much ductility, what's the deformation that you're going to need out of your structure. And so that is also a parameter that you are setting. And that does allow us, in general, to have more control of what is the predicted and what's the ductility that we're looking for. And at the end, in this example, you saw that we had about half, maybe even a little bit less, half of the seismic base shear. The difference, of course, is that the period is different, right, than what was the period in the code-based design as well. I didn't mention it, but code-based design was around 0.95. Here, our target was 1.5. So you are going to have more drift, but you're controlling and you're designing your whole structure for that level of drift. So in the end, the solution ended up being a solution that we didn't need 3 bays in each direction, or 3 times 2, we didn't need 6 bays. We would only need 2 bays. So with the same dimensions, we could reduce the overall amount of reinforcement, overall amount of concrete, volume of concrete in the structure. Maybe jumping straight to those comparisons. So in terms of what would be for this example, building 1, we had, just summarizing at the end there, base shear was about half, and we were able to get a good design there. We did a nonlinear time history analysis, set the corresponding hinges in the analysis, and then went through that to validate the performance that we were obtaining. Yes, because that shifted period, additional drift demands, it does mean that you have additional drift. So not only were we getting slightly higher drift, this is a code-based. You look the third line there, you see we had, after we ran this, only 1 earthquake, but just to have the same consistent comparison, we had, the design was at 2% and we got 2.25% drift. And then whoop, if you jump all the way down, you see that also our residual for this model, but the residual drift was about 0.5% interstory drift ratio. So the questions that you were asking in terms of drifts, right, as well, and if you are anticipating a little bit higher predictions. When you went to the objective-based design, the force was half, but changing the force to half did not double the interstory drift, right? It went from 2.25 to 2.8, and our residual drift going down there, it's about 1% residual interstory drift ratio in this model. So these would be the things to consider. However, this is a new design, and if you're detailing your sections can go way beyond what's the demand here for this design level. Actually, this was an MCE level shaking. So in summary, and I'll let then you explain for building 3, but in summary for building 1, we halved, so buildings design with objective-based design approach needs withstand nearly half the seismic base shear forces compared to the code-based design. In terms of this particular example, there was 2 design tweaks that we did in order to be able to design that building to about half. So I'll jump bullet 2 and 3. Bullet 4, that translated into cost savings in terms of concrete volume, rebar weight, by having the reduced amount of reinforced concrete and steel that we needed. And then the caveat and the thing to continue to think about is, yes, beam rotations in the objective-based design were higher than code-based design, but well within the limits of our life safety and collapse prevention as well.
Do you have any questions? Would it be possible to see once again the plastic hinges on the beams? There was a slide.
The plastic hinge behavior?
Yeah, that's what. Is this the what you obtained under the real earthquake excitation or?
Yeah, so this was the earthquake excitation that was scaled to the level of design.
Okay.
And this was actually to the level MCE.
And you applied this one?
Applied the same one.
And at the end, you obtained those plastic hinges?
Yes.
But he didn't allow hinges at the lower level. The analysis didn't allow, right?
Yes.
So the analysis assumed that there would be no hinges forming at the base of the column, which is not true. No, you can't prevent that. Is that what you?
Yeah. And after you have step-by-step integration, you got those. Did you achieve those plastic hinges over there? Or?
Yes.
You achieved that.
Yeah.
Well, but he got them because he didn't allow a plastic hinge to form at the base.
On the columns.
Yeah.
Yeah.
I mean, this is, the computer doesn't understand that that's not the way it's going to perform.
Yeah, but it is very interesting to have all the plastic hinges occurred on the beam.
In the 5-story building.
In the 5-story building.
Yeah. Of course, if it was a taller building, probably you'd have it concentrated at lower levels and not at the higher levels.
Well, I think you said in the first day presentation, you didn't assign specific plastic hinges at the ends of columns.
Right.
Just only you have used the track section.
Exactly, in this model.
It may be the reason of why you didn't have plastic hinges at
Could
the
be.
columns. Yeah, it means
We should also check in the next model. We should add that at first. Yeah, I was just going to show. I was just going to show one more thing here, if I may. I don't know where I get there. Where is the mouse? Okay, maybe that way. Yeah, here. So just in terms of overall, we just showed for this example, but in all the designs, we have several steps, and there's some flexibility in these steps, and I'll show where as well. So step 1 is where you define your target drift. Step 2 is where you're estimating the response spectral values, displacement response spectral values based on the target displacement and whatever gamma you're using to compute the single degree freedom spectral displacements. Then you set your target displacement, your target period. Then there's a trial phase where you're actually trying to match that period. And when you're going to match that period, that's where you're selecting your member sizes. And when selecting the member sizes, depending on your structural system, you also have flexibility here. This is an example where these equations are also derived analytically for a portal, the portal method and the portal system, where you have beams and columns hinging halfway. But if you have a different structural system, if you have a different assumed model, if you have shear walls, for example, this is where you would change and use a slightly different equation. But when you get here, because you have the target trial period and you have the displacements, what becomes the next problem is defining what your beam sizes are, and you can just, as Atta showed as well for the building 3, this is what's left, is what is the column sizes and beam sizes, and you try those to get the period there. So that's where you're doing some trials before you actually come to a period that's close to the period that you're designing. Then in terms of the capacity of the sections, that's where you also have flexibility. We showed an example, and Atta's going to show another. Let me go back to this equation. We showed a way to come and estimate the forces, starting with the elastic spectral acceleration, and then assuming a ductility factor that you can actually get out of the structural system and the detailing that you're going to put into the structure. So that is also where you're going to have a variable that you could play. So this is one way. The other way, as Atta showed, is you actually assign a capacity, right? And by assigning a capacity, you're defining what your base shear, because if you know your moment capacity of your hinges, you know what the corresponding base shear, right? That would be plastic analysis of sections. And if you know that base shear, that's the effective base shear that you're designing for, and then you make sure that you have enough deformation capacity in all your connections. So that's why, you know, Bob keeps saying that you don't really need to worry about the strength, right? It's because you have some flexibility in terms of the numbers that you're going to use to define the forces, and defining the capacity, you have the forces that you're getting. Then you have to make sure that your sections can take that deformation, right? So that's what you're playing with. I just wanted to reinforce that idea. I don't know if there's other questions, otherwise.
So this was the first example you are going to present. You have one more, I think.
Yeah.
Am I right? Yeah, but before we do that, is there any question coming from the audience? I think there is no question coming from that side. So you can pass the second example.
Atta, please.
Hello, everyone. Welcome back to the workshop. Professor Karadoğan, it's a pleasure. It's an honor to see you with us, sir. Thank you. My presentation will be about Building 3. It's a precast single-story building, what we call inverted pendulum, fixed at the bottom, pinned, hinged at the top. The building height is 8 meters, and the other dimensions of the buildings are as you see. So what I did is that about a few weeks ago, I wanted to try OBD on this building. So this is not a reference for OBD. So this is my attempt at OBD. So it is. I wanted to try it to have an interactive discussion about it. What I did is that I designed it according to our force-based Turkish code. So it's pretty straightforward. I determined member dimensions, and then I determined the quantities of the rebars according to force-based method. I'm not going to talk too detailed into that because that is relevant to the nonlinear analysis that I made. I will pass directly to the OBD methodology that I tried on this building. This is pretty straightforward, single degree of freedom building. So now I tried to go step by step on the OBD approach. So we define the seismicity by spectral velocity, not spectral acceleration. And this spectral velocity is the one that we used for all the buildings in the workshop building designs. So we define the spectral velocity, and the value is 1.5 meter over second at roughly around 0.5 a second period, and it is constant after that period. So using the methodology, I set up a 2% drift limit. Not a drift limit, but a drift target, actually. So it's not a limitation to check later, but it's a target that we want to achieve. So for an 8 meter high building, that corresponds to a 16 centimeters roof displacement. And since we have a single degree of freedom system, regardless of the Chopra expression, our gamma factor is 1. And for that reason, our spectral displacement target is 16 centimeters, 0.16 meters. So when I plug it into the expression to find the target period with 16 centimeters of target spectral displacement and 1.5 meter per second spectral velocity, I achieved my target period of 0.67 seconds. which was very close to the period I found in force-based design. So what I did is that I used our equation for, I didn't use any computer, by the way, while doing this. I used the equation in our code for period determination. So I have my fictive loads here, my material, my height of the building, the seismic mass. So the only unknown I have in this equation is the moment of inertia. That should be actually IG, not IE, because I already used the factor of 0.7. So I plugged it in our period calculation expression, and the target period there is 0.67 seconds, and I found the target moment of inertia to be 0.0165 meter over 4. And that corresponds to a section dimension of 667 millimeters. And I chose a 700 millimeter by 700 millimeter column dimension to achieve the target displacement. Now, up until now, since we are dealing with a relatively simple solution, simple building, everything was very similar to the force-based approach, because in the force-based approach we apply some forces and then we check the limitations for relative drift. So the member dimensions are exactly the same. What I did some research on this process was the force, because OBD says that force has no relation whatsoever should have no relation whatsoever with the structural behavior of the building. However, somewhere along the line we need forces. We need to quantify the reinforcement. We need to make some checks, some brittle failure checks. We need to design connections. So I made some research on how to define this force, and I basically halved the base shear that I calculated with the equivalent lateral force method. There is no written rule about this. There is no rule of dividing the seismic force by 2. But there was another reason to do this. I wanted it to correspond to roughly about 1.2% of column reinforcement. So in the force-based design, the column reinforcement in precast members is about 2.4%. Here we have about 1.2%. Another thing OBD says is that R and D factors we have in our code should not be imposed on the engineers, because buildings, some constant R factors cannot be used, because, for example, a column with a 1% reinforcement would not have the same R factor with a column with a 4% reinforcement. Correct me if I'm wrong. It would not have the same ductility as a column with a 4% reinforcement. So what I did is that I reduced by intuition the amount of longitudinal reinforcement, hence the moment capacity of the column. And what's important for me was I wanted to run nonlinear time history analysis on these two examples, because OBD says that when using force-based methodology, we are strengthening our buildings, but we are also strengthening the earthquake. We shouldn't do that. That's what OBD argues. So what I did was I ran nonlinear time history analysis for the two examples, the force-based design example and OBD example, to see the results, to evaluate the results in terms of relative story drifts, base shears, accelerations at the roof, and plastic hinge rotations. So I used 11 earthquake couples, all from Turkey. In total, 22 earthquake ground motions, and I scaled them according to our code. I won't go into too much detail about it. and I used SAP 2000 software to run the nonlinear time history analysis, and P delta effects were also taken into account. These results are in the bottom. You can see the average results in bold. These are relative story drifts. So, for example, for the force-based result, force-based design, we have 2.1% relative drift, and on the for the OBD design, we have 2.3% relative drift. Half the reinforcement, just a little bit increase in relative drifts, which is expected because plastic hinging occurs earlier on the behavior, and there's a similar result on the other direction. So my personal conclusion from this was that yes, there was an increase in the relative story drift, but it was within reasonable limits. So, for example, 2.1% to 2.3%, it's really small amount. And here you can see, and we can also visually see the residual displacements. So this is an example of relative story drift versus time for one of the earthquakes. And then I checked the roof acceleration at the roof. It was reduced in the OBD design. So I had 1.5 G at the for the strength-based methodology and 1.35 G for the OBD result. And on the other direction, I had a similar reduction. So it also confirmed for this particular building the argument that OBD can be used to reduce experienced accelerations. And this is the acceleration versus time plot for one of the events. Another thing I checked is the base shear. OBD says that, as far as I understand, OBD says that the designer should be able to control the force that is implemented to the building by controlling the capacity of the members. So reduction of the rebar comes from there. So when you reduce the reduction of the rebar, you reduce the base shear that the building is exposed to. And the results I obtained on the bottom, again, you see the average results. These are, by the way, the percentage of the base shear to the seismic weight of the building. I want to make some little comment here. They seem a little bit high. That is, according to my interpretation, maybe due to a little bit over design and maybe some over strength that is inherent in the structural model. So what we have here is, for the force-based design, we have 70% of the seismic weight as base shear. For the OBD, we have 55%. So it's a significant reduction. And on the other direction, we also have a similar reduction. And for the plastic rotations, they were increased, yes, which was expected, again, because we decreased the reinforcement significantly. But at least for this particular building, they again remained in the reasonable limits, 0.006 radians for force-based result, increased to 0.010 radian for OBD. So I think, at least for this building, it's an expected result for half the reinforcement. Again, this is just my attempt at OBD. This is not a reference for OBD design. Thank you.
Thank you very much. The results are very interesting. Do you have any question associated to this presentation? Yes, please go ahead.
just a couple of questions. What were the crack section stiffnesses that you used in the code-based design and the OBD model? Are they the same?
Effective
Stiffness of the columns. The multipliers.
70%, 0.7 for
0.7
both.
for both. Okay, so it's a little bit different than the code then. Because as far as I remember in the Turkish code, you have to you use
The expressions.
Yes.
No, I use 70%.
So it's just a comparison.
Yeah.
Okay. Do you have the moment curvature behavior of the columns?
Very sorry. Did you ask about the nonlinear analysis?
Yes.
No, I took 0.7. I didn't take the Turkish code for comparison.
So do you? I mean, is it possible if you have it? Do you have the moment curvature behavior of the columns that you used in the models? Just for a comparison, one of them has a higher yielding point.
The definition of plastic hinging that I defined to the model.
Yeah, if you have them.
Unfortunately, I don't have this in the document, but if you have a particular question, I can maybe.
No, I mean, what I think is because the code-based column, which has twice the reinforcement than the one with the OBD, should have a higher elastic rotation capacity. So in the end, it's interesting to see that the total drift ratios the rotations are quite similar. But the plastic rotations are nearly twice in the OBD. So there's a relation with the yielding moment of the cross sections. But it's good to see this because it's typical to precast buildings where we actually, if we do a code-based design, then we're supplying a high elastic rotation capacity to the system, even though we have a ductility level of 3 for these type of buildings. Something that I would like to mention and would like to hear the thoughts of the professors on this. Because these columns actually have twice the amount of rebars when compared to OBD, but then it has very high elastic rotation capacity, which we don't even use. So in a way, we're kind of maybe over-designing these systems a little bit. Would like to hear your opinions and also Professor Karadoğan's and Englekirk's thoughts on this. Thank you.
Go ahead.
One thing I would like to also add, thank you for the very on-point comments. One thing I would like to also add is that I'm thinking out loud. Connections are one of the main issues in precast concrete.
Yes, regardless of the technique.
Yeah.
The only point where the plastic hinging is at the bottom of the column in this case, so it's very particular. I mean, I'm not talking about the general of all the precast building types, but this is the most common type. I believe, which is constructed in Turkey. So it's what I comment is only on this example.
I understand.
So I'm not talking about the connections.
I understand. My personal comment would be that first of all, the R factor a factor of 3, since the column is the only structural member that resists the earthquake forces, the argument that 1% reinforced column would not have the same ductility with a 4% reinforced column, would have much more ductility, and vice versa for the 4% is relevant. So these results, of course, is for one building, but I think they indicate something. Another thing why I mentioned connections is that reducing base shear this way would maybe relax the forces that come to the connection. Yes, I mean, in the end, we find some forces and design connection accordingly, but maybe relaxing reducing the forces that act on the connections would help us a little bit to have better designed more, because sometimes such reactions come is that it's very difficult to place all those dowels. We need to sometimes lengthen the corbels. So maybe reducing the base here would also on the foundations. So that's how I would comment on that.
Are you able to give some numbers for the displacement ductility for your design and for the code design? Are you able to give that?
Unfortunately, I didn't check that.
You didn't check that. according to my opinion, we are over-designing the sections. This is what you are asking right now. Because it has been proven that the design, OBT design, is good enough to respond to the possible earthquakes. So you are over-designing the structures, according to my opinion.
Want me to comment?
Yes.
Well, it's been 20 years since I read my concrete book, but as I recall, there were initially studies of members that showed that the deformation level was independent of the amount of ductility in the member. In other words, you could get to a drift of or a displacement of 2 inches with 0.5% reinforcing, 1% reinforcing, 2% reinforcing, but they all reach the same amount. So all you're asking is whether there's a relationship between the ductility in the member and its response. And the answer to that is there really isn't. In other words, if you ask for the displacement of a beam to be 3 inches, that is the peak that you're going to get, whether it's reinforced with 1%, 2%, 3%. It's independent of the amount of reinforcing. If anything, it gets more brittle the more reinforcing you put in it. So that's, on that basis, we discount the impact of strength. I don't know if you can show the reinforcing that we dealt with in the 1970s, the one in my, I have plenty of slides. Does that explain your question? I mean, yeah, I mean, it doesn't matter. That's why we put 1% in, and the 1% works as well as the 2%, as well as the 3%. It's independent of the strength.
Should be in the second presentation, right? The
Yeah,
detail.
I think so. I just want to show the reinforcing that, yeah.
This one?
Yeah, that one. I have some that are even worse. But these were the force-based designs of the 1970s. And you can see these are double layers of number 11 bars. And the columns are double reinforced. And what it means is that it becomes much more brittle, but the deformation level remains the same. Anybody see anything different? I mean, we don't teach this anymore, do we?
We teach at the graduate level. We do teach,
yeah.
but I try to teach in reinforced concrete early on.
Yeah, go ahead.
But
If I may, so just to complement, the deformation level we're talking about is the corresponding yielding curvature is not a function of the capacity. So,
I just wanted to compare.
right. So, but if the yielding curvature is independent of capacity, it's one of those. I think Professor Priestley had a Milne lecture in 2003 where the opening is one of these myths and fallacies, and one of them is exactly that. So if we're starting with defining the yield curvature, if you have the same cross-section, the same height, if the yielding curvature is the same, the yielding displacement is the same, independently of having 1% or 2%, right? So that's the basis. Then, yes, as Ata mentioned, if you're going to 2%, 4%, the higher, the less ductile your section is going to be. So you may actually be hurting your building by adding additional reinforcement. So yes, I think I just wanted to reinforce that idea.
The ductility changes. The deformation doesn't. Can you imagine trying to build this? So, OBD, you design to 1% or 1.25%. Do you have any the pictures from of the failures or the problems with the
test results?
Yeah, the test results.
Should be here. This one, for example.
Yeah, this is the base of the column. It's 6% story drift. 6% building drift. Code asks you to limit it to 2.5, but if they're properly designed, they can go to that. This is spalling outside of the shell. Obviously, the strain in the concrete is going to exceed its elastic value, but it doesn't matter because it doesn't change the effective strength. Look at some of the other. Do you have some more in there? Yeah. Here's a typical example. The beams, this tie was supposed to be within 2 inches of the face. They left out the first one. Look what happened. So the member design doesn't change. The member design, you design for ductility, you design for shear capacity. The member design doesn't change. The only thing that changes is the amount of reinforcing requirement because you've taken the strength requirement out of the system. And the argument is that if you make it ductile, it's going to deform to the same level as if you make it less ductile and stronger. And that's the big thing that hurts precast concrete. Now you say, why do I care about precast concrete? It's because I lived in a city, Los Angeles, that had even more traffic than you have. So to get a concrete truck to a job site is sometimes, instead of having the 1 or 2 hour mixing time, it has 6 hours. And then you're faced with, well, do you send it back or don't you? So we have to get to precasting elements. Now the Paramount, I think you asked the question of the Paramount. Yeah. The whole reason for the Paramount was that we could build the whole thing in a yard, truck it in at night, put it on the site, and erect it during the daytime.
By the way, Paramount is a building, high-rise building, located in a very highly seismic place in San Francisco. So he is the designer of that building. Do you have any other questions, ladies and gentlemen? Yes, please go ahead.
Tabii.
Şöyle genel bir sorum var. Türkiye'deki mimari yaklaşım, yani mimarlarımızın genel yapı kültürüne olan yaklaşımları biraz da Türkiye'de betonarme yapım kültürüyle alakalı, yani işçilikle alakalı, buna bağlı bir şey sormak istiyorum. Bir görüş merak ediyorum. Şimdi biz yüksek binaları ya da çelik binaları, yani onlar daha özel oldukları için onları dışarıda tutuyorum. Anadolu'da yani yaygın olarak yapılan betonarme yapılardaki bir durum. Şimdi ben tasarım işçinin o günkü psikolojisi Türkiye'de. Yani meslektaşlarımın buna katılacağını düşünüyorum. Bu fotoğrafın burada olması da iyi oldu. Yanlış hatırlamıyorsam Profesör Englekirk burada bir işçilik hatasından bahsetmişti.
Bir tane etkiyi koymayı unutmuşlar.
Evet, evet. Biz bunun çok daha fazlasını yaşıyoruz maalesef. Yani kesme sürtünmesi hasarları, perde uç bölgelerinde, düğüm noktası hataları. Şimdi biz desek ki süneklik bazlı, yüksek süneklikli çerçeveler yapalım. Biraz daha etli kolonlar, etli kirişler seçelim. Bu sefer mimari buna uygun değil. Mimari kültür buna uygun değil. Dolayısıyla sınırlanıyoruz. Ve haliyle ben şahsen tasarım yaparken evet tabii ki yine yüksek sünek ama daha fazla, biraz daha rigid binalar, yani daha perdeli sistemler yapmayı tercih ediyorum. Bu konuda bizim yerimizde olsa Mr. Barbosa and Mr. Englekirk ne düşünür? Yani daha perdeli sistemler mi yoksa daha yüksek sünekli, yani daha çerçeveli binalar mı tercih eder? Tamam, istersen sonra.
Çevireceğim ama Faruk Hocam müsaadenizle çok ufak bir kendimde, çünkü çok sürekli tekrarlıkları, bizim birebir görüşmelerimizde de tekrarlıkları bir konu bu. Donatıyı %1.2 binanın tipolojisinden bağımsız olarak ya donatıyı çok fazla koymamak lazım diyorlar. Evet. Olabildiğince az. Dün mesela benim gösterdiğim bağlantı detayında, diğer bağlantı detaylarında şantiyede uygulanabilirliği olabildiğince basit, pratik olmalı. Zaten demin gösterdiği detay da oydu. Yani bunu hani bir donatı kafesi göstermişti ya, bunu kim uygulayacak, nasıl uygulayacak? Şantiyede hataya çok açık. O yüzden donatın azaltılmasının böyle bir avantajı da var diyorlar. Şimdi
ondan önce o zaman şöyle, kendi sunumumda da bahsetmiştim bundan özellikle. Yani minimum donatıyı da esas alıyoruz ama burada boyutlardan kaynaklı bir sorundan bahsediyorum aslında. Yani sünekliği yakalayacak minimum boyutlarda bir problem oluşuyor Türkiye'de. Bunu yakalasak bile işçilik bu sefer problemli bir hale geliyor. Yani aslında bu, o yüzden biraz daha perdeli sistemler mi tercih edilmeli ya da ne önerir?
Regarding the dimensions that we are required by the code to provide ductility and also the reinforcing details. We should be very careful in designing the reinforcing to account for any problems or mistakes in labor at the site. So in light of this discussion, also in terms of the dimensions of the building to provide ductility, and also in that regard, in terms of some constructability point of view, what would you say, how would OBD would come into play? Maybe by reducing rebars, you would have more constructible buildings. So how would you comment on that?
Well, the design of the components, I guess I suppose. You should design the components to behave as best you can. Typically, that means less reinforcing. If you show that beam column joint.
Beam column joint or the cage? This one?
That's good. Show the one back. Look at that. How easy is that to build? 4 bars and ties. Very easy to inspect. One can see that this is 2 inches away. That didn't get placed. There was a problem. So my offer to you is the less reinforcing, the easier it is to make sure that it is placed right. Look at the other one, what I call the 1970s. The picture of the reinforcing cage.
This one.
How easy is that to inspect? How easy is it to place? Can you imagine how long it would take to build that cage and interlace it with the column? Remember, those bars have to fit into that column cage. What a zoom. I wouldn't like to do it, would you? So if you take 2/3 of the reinforcing out, you get a better joint, and it's easier to check.
boyutlandırmadan çok donatıların azaltılmasının hem önerdikleri metodun mantığı açısından hem de uygulanabilirliği açısından çok önemli olduğunu söyledi.
Faruk Hocam, sizin görüşünüzü merak ediyorum mesela bu kendi sorumla alakalı.
Mimarlar yapı mühendislerini bir anlamda boyunlarından yakalamış durumda. Mimarların istediğini yapmayan yapı mühendisi değişecektir. SEP 2000'in yazarlarından patron Kaliforniya'da gördüğüm zaman bana demişti ki bütün sorumluluğu siz alıyorsunuz ama parayı mimarlar alıyor. Yani mimari isteklere her zaman evet demek doğru değil. Mühendislik bu asansımızı kullanarak olması gereken şeyleri cesaretle söylememiz lazım. İşi kaybetmek bile durumunda olsak. Ancak işin öbür tarafı da var. Mimar arkadaşlarımızın da estetiği bizi zorlayarak elde etmek yerine başka şeyler düşünüp estetiği yakalamaları lazım. Bir Amerikalı mimarla bir Türk mimarın isteklerini karşılaştırdığımızda bu çok açık olarak ortaya çıkıyor. Amerikalı mimarlar yapı mühendisinin isteklerini yerine getirmeye çalışırken Türk mühendisler Türk mimarların isteklerini yapmaya çalışarak yanlışlık ile sonuçlanan durumlara düşüyorlar. It is better to ask some additional questions related to the topics mentioned here or exemplified here, or if you have any other question in your mind related to the new design or retrofitting design. This is the chance now. We can ask, we can forward them. Okay, do you have any other questions?
Can I ask a question or comment?
Sure, Ercan.
Professor Barbosa, could you bring the page, the target formula?
From Professor Barbosa's presentation?
Anywhere, this equation.
Okay.
T equals to 2 pi type delta T over SV number.
Hocam bu arada Profesör Englekirk'ün acilen lavaboya gitmesi gerekti, affınızı istedi.
Okay. When we look at this equation, actually there are two critical components. The first one is delta T, which is representing the relative deformation capability of the building. And it's directly related with your decision, depending on your experience or experimental backgrounds, 2%, 2.5%, something like this. And the other important term is SV, and it represents the intensity of the earthquake, generally speaking. In that case, if the intensity of the earthquake is quite larger, you will get a large amount of SV. It means that you need more stiff building. Am I right? If the intensity of the earthquake is larger, in that case, probably you will get a large SV value from the spectral transformation. And you set this number in this equation, you will get a smaller number of target period. It means that more stiff structure. In that case, what's your decision for the selection of lateral load-bearing system? Shear wall type or frame type? Because we also need some plastic deformation capability to dissipate seismic energy in the structure. In that case, if you assign a specific shear walls, the plastic hinge is possibly located at the bottom end of the shear walls. But in other case, if you select load-bearing frame type load-bearing system, in that case, especially the plastic hinges will be located at the end of beams. Which one is better? And how do you control the lateral displacement capacity if you select this target period? A kind of dilemma, or you can make some estimation or true selection of lateral load bearing system.
Well, first of all, great question, and I think you hit the nail in terms of the flexibility that you have also in the design, because your target period is going to be driven by when you get to the selection and the matching of trial period to the specified period. That's where you have the flexibility in the design, be it in assigning the sections if you're using a frame, but if the sections start becoming so large, then you're probably not going to go to a frame system. You're probably going to go to a shear wall system. In terms of the trials that I have done, and following Bob Englekirk's book, where he has similar expressions both for the frames and for the walls in terms of estimating what those would be. If you start getting to 8, 10, 12 stories, that's when you're switching over to a shear wall system. You could have a dual system as well, but where you need additional stiffness because your trial periods are such where you're trying to match the displacement or you're trying to match the trial periods that you end up getting to a shear wall system. So that's essentially where, yes, I wouldn't say it's a dilemma. I would say it's part of the flexibility in the design as you're trying to do the trial and match, your trial period match the displacement, and if that makes sense to you. And maybe, just because Bob is back, maybe you want to repeat the question, see his opinion? Yeah, if you don't mind.
Well, my question is about the terms of the equation. Actually, there are two critical components. The first one is relative displacement, delta T. It's a selection depending on our experience in structural engineering. 2%, 2.5%, something like this. And also the other term, critical term, is representing the intensity of earthquake, SV. If we get very high intensity of earthquake, in that case, the term of SV will increase. The target displacement dependently decrease. To obtain more stiff structure for high intense earthquakes, something like this, by using this simple equation. In that case, what's your selection for lateral load bearing system? A shear wall type or a combination of shear wall and moment resting frame type system?
Well, as I think I mentioned, when people do the analysis of some of the buildings that I look at, they project accelerations of 2.5 G at the roof. The building that you design should be an isolator. When you design a building and you expect a ground acceleration of 0.6 G, why not make it 0.5 G or 0.3 G at the roof? So we isolate buildings, and we can do it with structures, with concrete structures. When I design a building, I look for an acceleration of the roof that is less than the ground input. So that to me is the objective. Have you ever experienced 2.5 G? You haven't been thrown in space yet. So maybe what we should do is put a few building officials on a trip to the moon and see what 2.5 G. I was in the Air Force, so I know what 2.5 G feels like.
Thank you. Thank you. We have 15 minutes more to continue that discussions. I will appreciate if you have some more questions.
Thank you. So I'll give you a history lesson. When I was young like you, concrete buildings were not allowed in California. The easy answer was no concrete. So when I moved to California, I started to introduce concrete. And now almost everything in Southern California is concrete. Why? Because steel, nobody knows how to work with it.
You have a question? No.
Are you laughing?
Yeah.
No. No. Historically, people have decided one of the biggest problems was you saw the ties on the concrete, and the code didn't require ties in the concrete. And I remember I was considered for the design of a concrete building along with another engineer. And his sales pitch, you know, the selling point was, I won't require any more codes than the concrete requires. So he had ties at 6 inches on center. After the Northridge earthquake, they were propping his building up with 10 by 10 pieces of wood. Have you ever seen a 16-story building supported by 16 by 12-inch posts? It was, the building almost came down. All of the columns in the lower floors were destroyed, basically. So it all lies in the detail, and it also lies in the engineer. And it's not equations, it's using your head. Can we go to the first example building?
That Andre has presented? The example building one, right?
Yeah, the one that everybody has designed.
Okay.
And it,
this part or another slide?
yeah, show the next one with the, no, with the, yeah, there we go. The importance of education is that the engineer must understand how to attain the objectives. How many of you are engineers? Oh, come on, more than that.
Hola.
What's wrong with this design? Well, how does that building behave? Like I say, I can't operate a phone, so. Here's a shear wall resisting or a frame braced here and here. What's the distance across here? 180 feet. What are you asking? The earthquake load to come from here and find out his way all the way over here? Huh? Because that's just not good sense, is it? So the difference between my design and other designs was I would break this down and put a bracing element here, here, here, distribute them. Why? Just makes sense. So the engineer has to learn to think. The computer doesn't understand. The computer doesn't care where you put the frames. You can put them next door as far as the computer is concerned. So it's very important that our teachers teach the fundamentals of behavior.
we need the floors, the diaphragms,
The diaphragm, yeah.
acting effectively to distribute the inertia forces to the lateral load resistance systems.
Yeah, I mean, the acceleration hits this piece of concrete as much as it does that one. But if this load has to travel all the way across there, the diaphragm has to be able to take it.
And especially if you have some gaps or voids in the diaphragms, it causes a big trouble.
Yeah.
If you don't have any additional question, I would like to ask a kind of personal interest question to you.
Mm-hmm.
Suppose that you are applying proportional loading to any frame you have here, and you are trying to look for the non-linear behavior of the frame. I mean, I'm talking about pushover, let's say.
Mm-hmm.
At each stage, you have one plastic hinge. You are changing the rigidity and you continue like that. If you wish, you can take into consideration the second order effects of the axial forces as well, as you did in your analysis. But I wonder whether there is any article or any design technique which takes into account the decreasing buckling safety of the structure. Because if you have two plastic hinges on both sides of a column, the buckling strength of that column will be 4 times smaller than fixed column. Not only the local buckling phenomenon, but the overall buckling phenomenon should be taken into consideration as well. But in our codes or in some other codes, this is neglected. What do you think about that?
What do I think? I think you should avoid it. The only place that we allow a plastic hinge is where we can't do anything about it, like at the base of the column. One of the things that happens when we do the objective-based design is when I design that column for that level, I design it use the same design here, here, here, here. So the higher mode effects don't come into it. There's nothing I can do about this except put some kind of base isolation or operated hinge or something like that. But I can design the base of the column to take 6%. I don't know if that answers your question, but I don't allow a hinge to occur in the frame. My favorite frame is a single bay, 2 columns, 1 beam. Beam absorbs the deformation, columns remain elastic. The fact that I reinforce everything the same means that I'm basically confining the hinge to the lower part, and I don't have to worry about higher modes. Because the first mode is going to cause the most deformation in any member, and if they're all designed the same, I don't have to worry about higher modes.
I am not asking the contribution of the higher modes, actually. I am asking the buckling phenomenon.
Buckling?
Buckling, or the loss of stability, or decreasing in buckling safety. Because the more you have plastic hinges, the lower, let's say for the frame, lower lateral rigidity. So we have to check whether a local or global buckling may occur in that structure. But do you have any method to take this one into consideration?
Yeah. Show the
plastic.
Let's see. What do I want to show? Oh, show the period and you know the test periods.
The shifting periods
Yeah,
from the test.
Yeah, what happens on
Okay.
the 6% drift?
Yeah, okay.
Yeah. Yeah.
This one, right?
Well, that initially, this is a good starting point. First of all, the concern is that this is the frequency or the inverse of the period. Here you see before anything has happened. So you get a frequency shift or period shift to here, to 1.6 seconds. So this is after the first test that we had. Now show the, see if we can see the time history or the, you know, the results of the
Comparison with the...
Yeah, that's good. In spite of the fact that you have a lot of damage, the period shift after this major earthquake is very little, very little. We've gone from a period of 1.6 to maybe 1.7, 1.8. So if you design your components to take the deformation, you're not going to get the deterioration that you're concerned about. Does that?
Maybe we can discuss this one a little bit more during the lunch period. Ladies and gentlemen, before I close the session, once again, I would like to thank the two professors we have here, Professor Emeritus Robert Englekirk and the young Professor Andre Barbosa. Thank you very much indeed for your contribution to this conference, to this seminar. And I personally learned a lot of things about the explanations. I didn't have a chance to attend here in the first 2 days, but you were here. So probably your gain is much more than my gain. So think about what it is said and let us compare with our code requirements. So this is going to be very important output for you. Professor Ercan, do you have anything else to add that, or what is your plan from now on? Are we going to have lunch? Are you going to present? Are you going to?
Thank you very much for your valuable contribution. And Professor Yalçın make closing remarks.
Okay, fine.
Just closing the workshop. And after that, probably we will get some group photo in front of the stages together.
Excellent.
Okay. Thank you.
Okay. So Yalçın, Cem Yalçın.
Evet, buradan da konuşabilirim. Daha samimi bir ortam belki de. Evet, organizasyon komitesi adına bütün katılımcılara, özellikle organizasyonu 2 aydır devam eden bu organizasyonda Ercan Hocama, Atay'a çok teşekkür ediyorum. Gerçekten çok çalıştılar. I'd like to thank, on behalf of the organizing committee, people who worked hard in the organizing of this whole event, primarily Dr. Ercan, Yüksel, and also Ata, Kulaksızoğlu. And we also wish aynı zamanda değerli misafirlerimize de teşekkürlerimi borç biliyorum. We would like to thank you also, Dr. Englekirk and Dr. Barbosa, for coming here, explaining and enlightening us with your methodologies. We learned a lot. Thank you very much for your comments and your presentations. Aynı zamanda bizimle birlikte binaları çözen 4 bina özelinde bu binalarla ilgili çözümler yapan mühendis arkadaşlarımızı da tebrik ediyorum, teşekkür ediyorum. Also, I'd like to thank to our other engineering staff or friends, colleagues who dearly worked in the solving of the 4 typical buildings, and so that we can compare the OBD with the strength-based design methodologies. And then they also made valuable contributions to this meeting. So overall, thank you again, and I hope you enjoyed your time, and I hope you will enjoy, probably, I don't know how long you're going to be staying here. Hopefully, you will enjoy Istanbul before summer, because after, I guess, closing the schools, the Istanbul's population will rise to another maybe a couple of million. So before that, make sure you visit all the nice places. And I'm sure Dr. Englekirk knows Istanbul probably better than I do. So again, thank you, and we'll proceed with our lunch, and then we'll adjourn from there. Thank you very much. And we're going to have a group photo, just to sort of make sure that we did our workshop. It's a proof. And so, where should we take the photo? Maybe. Okay, so. Sure, thing, yes.
Well, I'd like to thank Orta and tell you how this came about, because I called Orta after the earthquake last year and said, well, it looks like we have a problem, and aren't you using objective-based design? And he said, yes, I have the manual from objective-based design. Well, it was prepared by the committee, so it didn't come off. He said, I have one suggestion. Instead of making it objective-based design, make it objective-based, what did you call it? Computer-based design. Because at the end of the design process, it is required that you use an inelastic time history to justify your design. So what it devolved when it went through our code committees and everybody else, it came out as, oh, just plug something into the computer. If it works, it works. If it doesn't, change this member, change that member. But it took the engineer all out of the problem. It became, what do we call it? Artificial intelligence. It is not artificial intelligence. And it's up to all of us in the education business to ensure that people understand the fundamentals and what has to happen. It's just like the distribution of the shear walls in our example problem. So don't believe that the computer is going to replace you. Shall I tell you a funny story?
Yeah, go ahead.
Go ahead.
Yeah.
An engineer that I taught came to me one day a couple of years ago, and he said, my client is really disturbed. The building is way overpriced, and I don't know what to do. Can I hire you to fix it? And I said, no, I'm not in the engineering building. And he pleaded with me. He says, I'm going to lose the job if I can't bring the cost or save $2 million in the construction. So I said, oh, okay. I'll have to charge this person for my services. and it was a Chinese client. So they said, yes, go ahead. And I said, will you send me the money first? 6 months later, they figured that, well, here, we'll send you the money and you do it. So I looked at the design and I said, look, this bracing system does nothing, take it out. This bracing system does nothing, take it out. So they took it out, ran the computer again, saved $2 million, and that was the end of that. I had charged them $35,000 for my services. Took me half an hour. What is that? No, I guess I charged them 17, I don't remember, 17,000. It worked out to $35,000 an hour. So we have to get up with the lawyers. But the importance is that you cannot take the engineer out of the process. There's no such thing as artificial intelligence. And we have to develop that in our next generation and the generation after that.
It would be better to share the profit. Yeah, go ahead, please.
I just want to personally thank first the organizing committee. Thank you so much for having us. I don't have as many wise words as Bob Englekirk here, but it was very good to learn from you as well and learn everything you've been doing. And for me, it is my first time in Istanbul. I do hope it's not the last time, and I hope that this is the beginning of great collaborations. And thank you all so much for having us.
Arkadaşlar fotoğraf çekimi için sahneye rica edin.